In this video, we're going to take a look at analyzing process performance data and using z-scores to help us with that analysis. The specific learning objectives will be to understand process performance in relation to a specification limit or a customer need or a point of inspection. We'll take a look at how the z-score formula is derived and then can be used on process performance data. And then we'll use the z-score formula to help us better understand the population data that we work with. Okay, before we crack the egg of what is a z-score and what's the z-score formula all about, I thought we'd set up this video with a couple of problems related to analyzing process performance data. We'll work through these problems, and along the way we'll start to introduce the concepts related to z-scores and why they're an important aspect for analyzing performance data. So in the first problem that we have, we've got some performance data, and it's normally distributed with the mean equal to 100 and sigma equal to 10. And the question is, what's the percent of customer satisfaction if the one-sided upper specification limit is set at 110, 120, and 126. So before we work through this problem, I'm going to be using the empirical rule to help us with this information. And I encourage you, if you haven't had a chance to review the video about empirical rule or review some of the empirical rule problem and answer videos that we've already worked through, now's a good time to stop and take a look at that. But with that said, let's work through this problem. So I'm going to get a little bit more screen real estate right here. All right, I've got a little bit more space. Let's take a look at this problem. We've got some process performance data that was collected. It could be current state data on, I don't know, how long it takes to fulfill an order. It could be on how well we're cutting or crafting a part. It could be how long it takes to perform a series of steps that satisfy a customer or service request. So we've got this performance data, and it looks like it's population data because we're using mu and sigma as our descriptors for central tendency and spread. So that means population data, a lot of data, the last 6 months, the last year, the last 3 years worth of data. And what we found is that the central tendency or the mean is 100 and the standard deviation is 10. And like much of the business data that you collect, it's normally distributed. And I'll refer you to other videos that we've worked on to help you with tools to help you test if data is normally distributed, but the most common way is to plot out all that performance data, and does the histogram that's created look like a mounted hump, like a bell-shaped curve? And it looks like it does. So I'm going to draw this out. So we've got performance data normally distributed. We also know that there's a one-sided specification limit, a value that customers need performance to be at, and since it's one-sided, and an upper spec at or below. And the specification limit is at 110. So the USL, the upper specification limit is, in the first part here, set at 110. All right, so then what I want to know is, where does that upper specification limit fit on this picture? We already know where the mean is at 100. We know 10 units out is where standard deviation is. So I'm going to bring that line down, and that's at 110. I'll take that same distance on this side due to the rules of symmetry, and it's also at 90 right here. All right, and this is all kind of a review. Empirical rule gives us a lot of great information when we're taking a look at the percentage of data points that are plus or minus 1, 2, and 3 standard deviations. And we know through the empirical rule that rule of thumb is. Now let's go ahead and draw where that spec limit is. It's at 110. So if I draw my spec limit in, it's going to be right here. And the question is, what's the percent of customer satisfaction below that? Where anything on the left-hand side of that spec limit, that's where customers are satisfied. So we're really looking at this region right here. We're looking at this region in here. All right, well, this is a simple problem using the empirical rule because our spec limit is right at the one standard deviation line at 110. And so we know that everything below the mean is 50%. That's in this region. And everything in the +1 standard deviation area, that's 34%, half of 68. So we're talking about this region right here. So to answer the first part of question A, what's the percent of customers satisfied? We've got 84%. And that's a snap. We should all feel pretty comfortable working through those. And again, if that feels uncomfortable or is new to you, I'd refer you back to the empirical rule videos. Okay, the second question is, what if the spec limit is at 120? So I'm going to change my pen. We're going to take a look at spec at 120. Well, where would that fit on our picture here? Let's take a look. If this distance is 10, and that brings us out to 110. Let's add that same distance again. I'll bring this out right here and drop it down. That's another 10, or we're at 120. This is also then at the +2 sigma level. +1 sigma right here, and +2 right here. And we're at 120. And the question is, what if the spec is at 120? So that would mean our spec line would be right here. Customers are okay with waiting 120 seconds, or to process the claim in 120 minutes or less is all good, or any board that's cut to 120 inches or less, customers are happy with. That's what we're taking a look at now. If process performance operates at 100 with a standard deviation of 10 and the spec is at 120 right here, then the region where customers are satisfied would be this blue region that I'm going to color now. And if we do the math on that, we know everything from the red line is 84%, and due to the rules from the empirical rule, this is 13.6%. You could figure it out by you can figure it out by watching the empirical rule video, or some simple arithmetic shows if you take 95 minus the 68, divide by 2, you'll end up with this 13.6% after rounding issues. So the solution is 84 plus 13.6, or 97.6% of the time, we're meeting customer needs. Now, the last question is, what if the spec limit is at 126? So let's work through this in the same way that we've worked through the first two. Let's figure out where that line is. I know that if I go out one more standard deviation and go out to the +3 standard deviation line, that'll be at 130. But the specification limit that we're looking for here isn't at 130, it's at 126, which is right about there. Well, crud, if it was at 130, we could just use the empirical rule to figure out this slice between 120 and 130 and add it to our 97.6, and everything would be fine. But it's in between. I also don't think that I can just use a linear, well, we're 6/10 of the way there, so figure out where 130 is and go 6/10 of the way, because it's a little bit hard to see. But if I zoom in here, this part of the line, this part of the line right here, it's a little hard to see, but it's not a straight line. There's a little bit of curve to it. So we couldn't even kind of extrapolate it. We're stumped. And that is the dilemma when we're working with performance data that's normally distributed and we are comparing a specification limit. If the spec limit lands exactly on the 0, 1, 2, plus or minus 3 standard deviation lines, empirical rule solves our problem. But if it doesn't, if it lands somewhere in between, like at 126, we're out of luck unless we pull together a more powerful tool or a more powerful rule of thumb. I think you know where I'm going here. The more powerful tool that we'll use to solve this question about 126 is going to be z-scores. Let's take a look at problem B. All right, in part B, I've got a little more screen real estate here, and we're ready to work through it. We've got process performance data that was collected. Again, it's normally distributed, which is what most business data will be. The same mean and standard deviation as in part A problem. So I'm going to draw this. It'll look something like... All right, so I've got the data drawn out in the following fashion, and now our spec limit is two-sided. So we've got an upper and lower spec, and they are, in this case, at 110 and 90. The previous example with a one-sided spec, common in service environments, two-sided specs, very common in production and manufacturing environments. You know, you can't cut it too small, and it can't be too big. It just won't fit. So the specs are at 110 and 90. Well, now this is back to our empirical rule. This is a pretty easy problem because we know that it was 34% on one side, 34% on the other. So the two together, we're looking at 68%. That's a snap, 68%. The next part was what about if the spec was at 120 and 80? Let's take a look at that. This is just, again, back to simple empirical rule. We're at plus or minus 2 standard deviations. So this region right in here is going to be 95. And now the next question is, what if we're at 115 and 110? Oh, well, let's take a look. We know that 110 is located right here, and 115 is located right here. So really, we're looking for this region in green right between the two spec limits. Well, the empirical rule doesn't really help us with that. If we went out from the +1 to the +2, we could do it. If we were doing whole standard deviations, we'd have an answer. But again, we're out of luck here. We don't really have a way using the empirical rule. Whether you've got one-sided specs or two-sided specs, the empirical rule starts to break down if your point of inspection, the spec limits, are not exactly at those +1, +2, +3 standard deviations. Let's take a look at part C next. It looks like we're getting pretty close to our 15-minute time limit. So to honor our promise to keep it at 15 minutes or less, I'll finish up these sets of problems in a second part of this video. We'll take a look at solving the rest of these problems and introducing the z-score formula and using z-score formulas to satisfy these trickier problems that the empirical rule doesn't resolve for us. We'll see you in part 2.